Okay, so in this video, we're going to look at setting up spring problems. This is going to be a two-parter. There will be sort of the general setup, and then we will come back and we will look at properties and do another worked example in the second video. So in this case, we want to first just think about spring problems in general. Spring problems are derived from physics using a balance of forces approach. Gravity is typically on one side, mass and acceleration, and the damping forces and the Hooke's law, spring forces, and if there are any driving forces, go on the other side of the equation to balance these things out. Another thing to kind of keep in mind is that we're going to use these. Sometimes we'll be given these coefficients directly in problems, and sometimes we will have to solve for them. But these are our basic components of the force. Now, one additional thing that we have to kind of keep in mind is that sometimes we're dealing in SI units, and sometimes we're dealing in English or imperial units. This is, the situation we have. We're in the US, and so you're going to encounter both of them. Now, in the English units, typically you're given force, which is in pounds. If you need mass, you have to convert it to slugs or some other unit that is typically used in these problems. Feet are this typical unit of distance and so forth. In SI, when you're doing scientific standards, then you tend to use things like meters and newtons and kilograms and so forth. So force are pounds or newtons. If you are in like astrophysics, you may have not KMS SI, but you may have CGS SI, in which case you may have dynes. I'm going to, and grams and centimeters, I'm going to avoid those somewhat as much as possible. But in principle, they kind of work the same way. You need to match your units, though, so that everything is consistent. Mass in English units are called slugs. And you have to typically solve these from the pounds, the weight, using Earth gravity. Units of mass and SI units are kilograms. If you want force, you typically have to employ gravity to get to newtons. Units of distance are typically feet, because gravity is feet per 32 feet per second squared. And then in SI, they are typically in meters, again, unless you're in CGS, in which case they're centimeters. We're going to stick with standard meters. And then the one thing that's the same in both cases is typically units of seconds. Now, it's worth noting that in most, especially math textbook problems, you don't want to get too precise in terms of your decimal places. Problems are set up, if they are going to be decent, as 9.8 meters squared. That is obviously, you could take it out to be more accurate, 9.81 meters per second squared, but then you will get slightly different answers than you might expect in a textbook. Same thing for gravitational acceleration. Rounded to the nearest whole foot, it's 32 feet per second squared. If you add additional decimals on it, in the real world, you might get a more precise result, but in a textbook circumstance situation, you may in fact just not get total agreement with your answer. And so know your audience is what my suggestion would be. When we have to do conversions between mass and force, force is equal to mass times gravity, or force over gravity is equal to mass. Again, sometimes we do this because in the English unit problems, we're given force in pounds, weight, and that has to be converted to mass units for our problem. Now, we want to sort of look at some examples of how some of these things are stated inside problems, and so how to solve for them and identify them. So we're going to take each of these components out and kind of look at specific examples before we actually go to a problem. So a problem might state a mass weighing 2 pounds stretches a spring 6 inches. So this mass is given in pounds. And so we have to convert it to the mass unit in that system by dividing by gravity. 1/16 of a slug is the mass. That is the coefficient that would go into our spring equation for mass, for the M portion. A mass of 100 grams stretches a spring 5 centimeters. This is in grams instead of kilograms. If you want to convert to KMS instead of CGS, you would have to multiply or divide by 1,000 in order to get kilograms. A mass of 2 kilograms is hung for the spring. You don't need any conversion. You've already been given the mass. Much rarer, a mass of 1 slug is hung from a spring. Again, no conversion needed, but this doesn't happen very often because if you've never heard of the term slug before, there's a reason for that. It's because it doesn't get used very often, except in these weird contexts. Now, if we're finding the damping constant, that's the gamma that was in our previous equation, then typically these are just sort of given to you straightforwardly, although they might not be. The mass is attached to a viscous damper with a damping constant of 400 dynes seconds per centimeter. Don't worry about the units other than telling you which system of measurement that you're in. This is in the CGS SI, and so the force unit is in dynes as opposed to newtons. You can do this conversion, but if you're seeing something like dynes here, it's probably intended to be done in the CGS system. And this is somewhat uncommon because we're usually steering people into physics, and astrophysics is a little weird, but here, though, the damping constant is already provided. Gamma is just told to you. If there is no damping, then obviously the damping constant is 0. If they don't say anything about damping, you can also assume that it is equal to 0. A mass is also attached to a viscous damper that exerts a force of 3 newtons when the velocity of the mass is 5 meters per second. So in this scenario, we're going to use this formula for the damping force, which is gamma times the velocity. They've given us the velocity is 5 meters per second. They've given us a force of 3 newtons. That goes on that side. And then you solve for gamma from there. You can put that into your equation. The motion takes place in a medium that offers a resistance numerically equal to the magnitude of the instantaneous velocity. Instantaneous velocity is just the y prime, it's v. And saying that the resistance, the force, is numerically equal is just to say that gamma is 1. And then finally, the mass is attached to a dash pot mechanism. That's another way of dampening something that has a damping constant of 0.25 pounds per second per foot. Dash pot is a damping mechanism. The damping constant is given in the correct units in this scenario for the problem. So you can just put it in. If you're given English units, you do not need to convert to metric or vice versa for that matter. It is expected that your answer will be in the appropriate units for the original problem. Now, the spring constant is much more commonly something that you have to solve for. So here we have a spring mass system has a spring constant of 3 newtons per meter. So there's nothing to do here. They gave you K. So K is 3. This, again, doesn't happen all that often. A spring is stretched 6 inches by a mass that weighs 8 pounds. So 8 pounds is the force, and 6 inches is half a foot. So you put this into your spring Hooke's law formula, and you find K to be 16. That can go into your differential equation. A mass of 5 kilograms stretches a spring 10 centimeters. We have the real mass. To get the force, we multiply by 9.8. That can go into our Hooke's law equation, and along with 10 centimeters or 1/10 of a meter, and we get 490. A spring is stretched 10 centimeters by a force of 3 newtons. So this is a slightly less complicated version of the previous example. We already have the force. but we still have to deal with the 10 centimeters, converting it to meters. And finally, a mass of 200 grams stretches a spring 5 centimeters. If you want to be in KMS units and not in dynes, then you're going to need to do some conversions. If you're working in dynes, the gravitational constant is 980 centimeters per second squared. And so your force would be 19,600 dynes, and then you would put that into your equation and you would get a constant of that 3,920. Again, these dynes and CGS type units are somewhat more uncommon, but they do show up from time to time, usually later on in the example problems and the practice exercises, sometimes just to, make sure you're paying attention. The forcing term, most forcing terms, they will simply tell you what it is. So if the system is driven by an external force of blah, 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 then you have it. It's in newtons, but they will just give you the function. And then finally, initial conditions. We also need these in order to finish solving our problem. So if the mass is pulled down 3 inches and then released, so pulled down 3 inches is 1/4 of a foot. Down is the negative y direction. As a math person, I typically stick with the negative is down, positive is up. But these are arbitrary orientations. So as long as you are consistent, you could choose up to be negative and down to be positive. But I'm going to go with down is negative. And then released means there's no initial velocity. You were just holding it there and then you let go. So your y prime of 0 would be 0. If the mass is set in motion from its equilibrium position with initial velocity of 3 centimeters per second, so from the equilibrium position means y of 0 is 0. But the initial velocity of 3 centimeters per second means, again, in the units of meters, y prime of 0 is 0.03. If, again, you're using CGS units, then this is already in the centimeters, and you would just call it y prime of 0 is 3. So again, you have to worry about being consistent with which system you're working in. All right, so in order to set up our differential equation, as I previously noted, we have our acceleration, our gravity typically on one side, and then we have our damping and our Hooke's law and our forcing terms balanced out on the other side of the equation. To solve this in differential equations, we typically move everything but the forcing term to the other side. And so all these were pulling in the opposite direction of the gravity. And so now that they're all on the same side of the equation, they're adding to each other. This is one of the reasons why we frequently get complex solutions. If there were more negatives, we would be much less likely to get complex solutions, but we get a lot of them. So this is our sort of standard way of setting up the differential equation. We went through a lot of those examples because we need mass, not force. We need the damping constant, not the velocity. But it goes with the velocity. We need the Hooke's law constant, the spring constant. We need to be able to solve for those things in order to set up our equation. So let's look at one example where we set up the equation and we solve. And then we will talk about some additional things and solve a second example in the next video. So here, our first example, I tried to keep it relatively simple so that it would be easy after our long introduction to get to a solution. So a mass weighing 2 pounds stretches a spring 6 inches. If the mass is pulled down an additional 3 inches and then released, and if there is no damping, determine the position of the mass at any time t. Now you can change the variable that you're using here. You can call it y, you can call it u, whatever. Find the frequency, period, and amplitude of the motion. So to find the mass, so first we have to find the equation in order to find any of these things. To find the mass, this is because this is in pounds, we're going to divide by the gravitational constant and get our 1/16 of a slug. So in our equation, that's our 1/16 y double prime. The damping constant is 0 since they told us there is no damping. And to find the spring, the Hooke's law, the spring constant, we have 2 pounds is the force, 6 inches is the amount that it was stretched, that's half a foot. And that gives us, we plug this in, the spring constant is 4. So that goes into our equation. So remember, gamma is 0, m is 1/16, k is 4, and we have no forcing term since it's not mentioned in the problem. Now, our initial conditions are also provided. It's pulled down an additional 3 inches. So that was one of the examples that we did earlier. That's y of 0 is -1/4, and then it's released. So y prime of 0 is 0. Now, if we solve this, we're going to use our characteristic equation, which we're assuming the solution is of the form e to the rt, or e to the rx, depending which variable you choose to use. And then when you take your derivatives, the y double prime gets replaced with r squared, and the y doesn't have any r out front. It's just the constant. And then we solve this by multiplying by 16 everywhere. R squared is plus 64 is equal to 0, or r is plus and minus 8i. And so we put our complex values into sine and cosine, a cosine 8t and b sine 8t. And then using our initial conditions, we can then solve our y of 0 is -1/4. That's the down 3 inches. And released is our y prime of 0 is 0. So in the first case, we're going to plug t equals 0 in for t, and we're going to set this equal to -1/4. Sine of 0 is 0, so cosine of 0 is 1. We're just left with a is equal to -1/4. And then we take a derivative and we set that equal to 0. We've got chain rules happening. So -1/4 cosine 8t becomes 8 comes out, sine flips, we get 2 sine 8t, and then sine, we get an 8 come out, but no sign change. And then we plug in 0. Sine of 0 is 0, cosine of 0 is 1, and that's all equal to 0, and we end up with b equals 0. So y is equal to -1/4 cosine 8t. That is our function. Now, this problem asks us to find the frequency, period, and amplitude. And so to do that, typically, again, this is the natural frequency because there's no damping. The amplitude is going to be given by a squared plus b squared all under the square root. So essentially like the polar coordinate transformation, or complex number transformations, the magnitude. In this case, since we only have -1/4, we just take the absolute value of that and we get 1/4. Because if you plug it into this, b is 0, and you just end up with -1/4 squared, which becomes positive, and then you square root it. And so you get the positive value. The amplitude is 1/4. The frequency is just the omega in the expression. So it is the constant multiplying t inside the trig function. So that's 8. And then the period is 2 pi over omega. And so you end up with, in this case, pi over 4. Now, if we have damping, then the frequency and the period become the quasi-frequency and the quasi-period, and the amplitude is changing as the problem decays. They are found basically the same way, the frequency and the period. They're just simply called the quasi-frequency and the quasi-period when damping is involved. Okay, so let's stop here and then we'll save the second example for video 2.